Okay, so last video for the unit. Hope you guys have been doing a good job of self-teaching here. So this is not too bad, catalysts. There's a few things on here that you might, I don't know, I think that overall what you need to know about catalysts is really not all that difficult, okay? So here's the idea behind a catalyst. It basically speeds up the rate of a chemical reaction. We've already talked about that in the first section. But the way it does this is by lowering the activation energy, okay? And there are actually a couple of different ways that this occurs. And you know what? I think I actually want to talk about this. So let me pause this for a second. I'll pull up the, unless I already, no, I don't have it up. I'll pull up the AP chemistry thing. Okay, so here it is. Essential knowledge 4D1 basically summarizes a couple of the ways that catalysts speed up reaction rate. And A says a catalyst can stabilize a transition state, which lowers the activation energy. So if you remember from the last section when they talked about transition states, basically that's the in-between. So you've got this, and it's basically what has to happen in order for the reaction to occur. So a transition state, for example, maybe I should just back up and show this to you. If you're looking at a transition state, you're looking at something like, back quite a bit up here. Okay, here we go. So transition state or activated complex, we're talking about this right here, okay? So one way a catalyst might work, it might stabilize that transition state, make it a little bit more stable, so that it can react more quickly, okay? So that it can essentially make it easier for that transition state to go from the beginning to the end, okay? So if it stabilizes the transition state, essentially more stable equals lower potential energy, okay? So stabilize the transition state, you have a lower potential energy. In other words, there's less of a hill to get over for the reaction to occur, all right? So it's just going to lower that activation energy in that way. Now, the other way this can occur, catalysts can also participate in the formation of a new reaction intermediate, okay? So it can actually help form a different intermediate. In other words, it provides a different mechanism, okay? So we talked yesterday about mechanisms and how there are different possibilities sometimes. Well, if the catalyst is there, a lot of times maybe there's a new mechanism possible, okay, that wasn't there before. A good example of this, yesterday we talked about ozone for just a brief amount of time. Let me get to the mechanism slides here. I think we talked about ozone. Yeah, there we go. Okay, so here's a proposal for the conversion of ozone into O2. So that breaks down, if it's just ozone in the atmosphere. However, if you've got something like NO in the atmosphere, that can be a catalyst for this reaction. So you have NO, right? So now you've got O3 plus NO instead. This reaction will actually occur more quickly. There's a new mechanism there that's possible, okay? And so what you end up with there, essentially, the overall reaction is going to be NO2 plus O2. So NO is one of those pollutants that we don't necessarily want to put up into the atmosphere because it can catalyze the decomposition of ozone. It can speed up the breakdown of ozone, okay? Which is not necessarily a good thing in our upper atmosphere because the ozone is what absorbs a lot of that UV radiation that's coming in, all right? So that's kind of the idea with these catalysts. They can do one of those two things typically. Either they lower that activation energy. Just went too far. Oh, sorry, I'm on the wrong screen again. A little disorganized this morning. I did not expect this to be off again. So it can either stabilize the transition state, so that lowers the activation energy, or it can actually provide a new pathway with a lower activation energy, okay, so that this reaction can happen more quickly. if there's less of a hill to get over, then you're going to be able to get over the hill more quickly, and the reaction is going to happen faster. Okay, so the graph looks like this, essentially. Okay, so let's say that your initial reaction looked like this. Okay, this is the activation energy for that reaction. That's the hill you have to get over. Well, let's say, now in this case, it looks like what's happening here is that we're forming a different intermediate, okay? So it's not just lowering the activation energy here by stabilizing the transition state. It's actually forming a different intermediate. So now we kind of end up with two steps in this reaction, but both of the steps have a lower activation energy than the initial, so this reaction can now occur more quickly, okay? So that's kind of the idea with the catalyst. And so you just need to know how those graphs look, because I almost guarantee you they will ask you a question based on a graph where they will ask you to draw an energy profile for a reaction, a catalyzed reaction and an uncatalyzed reaction, okay? Or maybe they'll give you this one and they'll say, now draw a sketch of what it would look like if the reaction had a catalyst. And then you'd have to show that you understand that the activation energy is lower when you have a catalyst in the reaction. Okay? So that's basically how that works. Two types of catalysts, homogeneous and heterogeneous. I think my other set of slides here, well, let's see. Yeah, I think my other set of slides do a little bit better job of showing this. Okay, here's that again. Okay, so another example of a catalyzed reaction where, again, it looks like a two-stepper rather than a single-step reaction. Okay, so this basically says the same thing that they say on the AP exam. Increase the rate of reaction by decreasing activation energy or changing the mechanism. So homogeneous catalysts are not all that difficult to envision. I think in the book, the example of the homogeneous catalyst they give you is maybe hydrogen peroxide. Let me look that up to make sure that I'm telling you right on that. So for a homogeneous catalyst, no, the one that they give you is sodium bromide on page 605. Okay, so that's a homogeneous catalyst, and basically homogeneous, it just means that the catalyst is in the same phase as the reaction that's occurring. So if your reaction is aqueous, then the catalyst is also aqueous. All right, so it's, you know, a lot of times that kind of catalyst is just happening in solution. We did one of these last year, the elephant toothpaste, if you remember that. I had a catalyst in there. I believe it might have been sodium bromide in that one. And so what that does is it actually, or potassium bromide, I think it might have been potassium bromide. But that reaction, or that catalyst, speeds up the decomposition of hydrogen peroxide, H2O2, into water and oxygen. And so, but that's a homogeneous catalyst because it's all happening in aqueous solution, so it's all basically the same state of matter. Okay. What you'd probably be less familiar with is maybe a heterogeneous catalyst. Heterogeneous catalyst, you've got, a lot of times you will have like a solid catalyst, okay, and then you may have gas molecules coming in and essentially docking on the solid, and based on where they dock on the solid, it's easier for them to react. So they use the solid surface to react, and then they go away again. Okay, so you can see the example here. You've got, this is ethane, I believe. Looks like 2 carbons here. Ethene, sorry, C2H4. Okay, so you've got ethene and hydrogen, okay? And the solid surface will allow those hydrogens to separate from one another, essentially, so that they can attach onto different places on the ethene, and then that changes it to ethane, okay, where they just have carbon-carbon single bonds. So this is actually hydrogenation is what's happening here. For those of you who have taken any of the Project Lead the Way classes, the biomed classes, what's happening here is essentially a double bond is being hydrogenated, so you're putting more hydrogens into this thing, and so you end up with a saturated organic compound with as many hydrogens as are possible. Okay, so that's kind of the idea here. But this solid surface here, this solid carbon surface, allows for a quicker hydrogenation process in this particular example. Okay. Another good example of that they give in the book that I did specifically say you need to look at is a catalytic converter. That's on page 608. You need to make sure you understand how the catalytic converters work. And it's the same basic idea where you've got a gas from your exhaust that is passing over a solid surface, and it's causing some reactions to happen very quickly that decrease the amount of toxic pollutants that you're putting out of your tailpipe. Okay. Another really big example of catalysts, important example, is enzymes. Okay. Enzymes, that's just the name for a catalyst in a biological system. Okay. Catalase is a good example of this. I believe they explain in the book that this is some sort of liver cells that are ground up, or liver tissue that's ground up, I guess, and that contains that catalase in it. If you put that in with hydrogen peroxide, then it will cause it to break up very quickly. Catalase's only job in the body is to break down hydrogen peroxide more quickly. Okay, so that's a specific enzyme in your body that just breaks down hydrogen peroxide, speeds up that reaction. You have all kinds of these enzymes in your body. They are incredibly important. Without them, our body would not be able to do chemical reactions as quickly as it needs to. Okay? So then you've got the idea of the enzyme, the substrate, the enzyme-substrate complex, and then you end up with your products at the end. Okay? And notice the enzyme has not changed because a catalyst does not change in the course of a chemical reaction. It just helps the reaction to occur. All right? So essentially here what the enzyme is doing is it's helping this thing to break apart. It's allowing it to break apart more easily. Okay? So that's kind of the idea there. Substrate fits into the active site much like a key fits into a lock. So that's why each enzyme is specific to one particular reaction, because they have this specific shape. So they will be specific to certain molecules. They will either help them to come together or break apart. Okay, and that's it on the enzyme part of things. Now I do want to show you one other thing on the AP curriculum here. They give 3 different categories of catalysts. Okay, surface catalyst we talked about. Oops. Surface catalyst is like a heterogeneous catalyst. That's essentially what that is. Okay, so catalytic converter, the one that I showed you with the hydrogenation, those are examples of surface catalysts. Okay, enzymes we just talked about. Okay. And you don't need to know a ton about that, but there is some terminology there. You might want to go over the vocab that's in the reading guide just to make sure that you know all that vocab associated with enzymes so that you're familiar with it. The one that we didn't really talk about is acid-base catalysis. Now, basically, I think what you need to know about acid-base catalysts is exactly what they tell you here. It's not in your book. It's not in the notes. It's not on your reading guide, really, other than just a mention of it, you know, because you're reading Essential Knowledge 4D2A. Basically, what's happening here is there are certain organic reactions, and they're typically organic reactions that will occur much faster in the presence of either an acidic solution or a basic solution, just depending. Okay, and you just need to understand that basically certain reactions will happen a lot faster if you put them in the presence of an acid or a base. So this acid-base catalysis usually happens in organic reactions in our bodies. Okay, not even necessarily in our bodies. They can happen in organic reactions in labs. But there are common examples of this. The ones that I looked at were very, very complicated as far as their mechanisms. It's more along the lines of something you learn in an organic chemistry class. So I don't think they're going to hold you responsible for that. But you do just need to know that that is a type of catalyst that can speed up or slow down a chemical reaction. Okay? All right, and then one more thing here that I want to mention. They love to ask this question on the AP exam, or they used to love it. I don't know if they're still going to. But the question is, and I'm going to give you some practice on this in class, is they will give you a mechanism. They'll give you a couple of steps, elementary steps in a mechanism, and then they'll ask you about one of the species in the mechanism, and they'll say, is this a catalyst or is it an intermediate? Okay. So, for example, here is the Br minus a catalyst or an intermediate in the following mechanism. Okay. Now, here's how you can tell. With an intermediate, we've been talking about this. An intermediate is something that gets formed in the first step of the mechanism, usually the first step. If there's like 3 or 4 steps in the mechanism, it might not be the first step. But an intermediate gets formed in the course of the reaction, in the course of the mechanism itself, and then it's going to get used up again. Okay? So there actually is an intermediate in this one, and it's Br2. So you guys can see here, Br2 gets formed in step 1, and then it gets used up in step 2. So that's actually going to cancel out. When you write the overall reaction, it's like it was never there. Okay? That's an intermediate. Now, a catalyst, what you're looking for with a catalyst is something that doesn't get used up in the chemical reaction, but it has to be present at the beginning in order for the reaction to happen, or in order for it to happen quickly. Okay? So what you're looking for essentially is something like Br minus. Okay? Br minus is something we add to the reaction at the very beginning, but notice at the end of the reaction it's still there. So it didn't really do anything. Okay? I mean, it did something, but it didn't go away. Okay? It didn't get used up in the chemical reaction. It's still there at the end. So theoretically, you could use it again to further catalyze this reaction. Okay? And notice what this reaction is. This is the decomposition of hydrogen peroxide using bromine. So that goes back to the elfin toothpaste thing I was talking about earlier. So that's kind of the idea of the difference between a catalyst or intermediate. Let me see if I have any more examples here. Okay, so another example, and they'll just ask you this question straight out. And again, I'll give you some practice on this. It's an easy question, so I think you should be able to get it. Is the HI a catalyst or an intermediate in the following mechanism? Okay, so then again, you just look at it. Okay, HI is formed in the first step, used up in the second step. Okay, so if I write this mechanism, it's like it was never there. Or I write the overall reaction, it's like it was never there. Okay, now I will say, if you're writing the overall reaction for this first one as well, then yeah, the bromine's going to cancel out, so it's kind of like that was never there either. What we usually do in those cases is if we have a catalyst, something that we need in order to help the reaction to occur, help it to happen more quickly, then we will actually put the catalyst over the arrow, okay? And so then that shows, and I don't know that you need the 2 necessarily, but that shows, okay, we're using this bromide here as a catalyst for this reaction. And actually, you know, there's 2 catalysts here. You also have the H plus that you start out with and doesn't get used up. So technically, our catalyst for this one would probably be HBr. Okay. All right. So that's kind of the idea of the difference between a catalyst and an intermediate. That's all I really need to say about that. So just make sure that you understand all of that, okay? Catalysts are not all that bad. What you need to know about them is not that much in detail. So, all right. Hopefully, we will see you in class tomorrow, unless some other crazy act of nature happens. Enjoy your snow day.